the OLS notebook. So if I didn't share my screen, I think it will still show what was on the screen behind me, maybe. We'll see. Anyway, this is just backup. So we have about 20 minutes. Let me see how far I can get. So we'll just, same structure as always. We import the modules. They're NumPy, Pandas, GeoPandas, matplotlib to do the diagnostic plots, libpysal to open the weights files. We're only going to open a kernel weights file to do the hack standard errors if we get to it. And we have the weights module to fix the kernel weights, if you remember. And then we import from SPReg. This is the first time we actually import from SPReg. And rather than writing xpreg dot something every time, we import OLS and then two specific function, fstatistics and wall tests. And then this is for to get the output the way I like it. Okay, we're importing these. And then again, I summarize the functionality that we're going to be using and the input files. It's always the same thing. After a while, in fact, in future notebooks, I will group all this in one cell. So you do Control Enter and we're good to go. So these are the files. It's the Chicago SDOE shapefile that we used before and the triangular kernel weights, and then an output file if you want to make output, which is optional. And the variable names, this is initially in what I call legacy SPReg, there were no such things as reading shapefiles, and pandas didn't exist yet. So we had to write our own code to pull the data out of DBase files. So we would pull them out of DBase files and turn them into NumPy arrays and pass that to SPReg. That's the old way. Since probably about 6 months, you don't have to do that anymore. And SPReg can take a Pandas series, GeoPandas series, and Pandas and GeoPandas data frames as inputs, and then turns it into NumPy arrays under the hood. But what you still need is the variable names to pull the right columns from these data frames. Remember, we saw that the variables are called columns in Pandas and GeoPandas. So the way I set this up is I specify these variable names ahead of time, and then I just create little data frames, and those get passed to SPReg. I'll show you in a few minutes, there's another way of doing it, where you don't pass it, you don't set it up ahead of time, but you pass the data frames to SPReg as such. It's a matter of preference. For my purposes, this is a lot easier because I set it all up on the top, and then I only refer to Y and X later on, right? So these are the variable names. The dependent variable is this index measuring premature mortality. A higher value is a worse health outcome. Then I have two ethnic variables, percent Black population, percent Hispanic population, and then an economic hardship index. So again, higher value is worse condition. And the example is what is called the immigrant paradox. I won't dwell on that too much, but I'll show you why you have to be careful when you're doing regressions. So we're reading, this is always the same thing. So as I said, in future cases, I will put this all together. So you read this shapefile, and then just to make sure that we have it, here are the variable names. We're going to read the weights, and then we're going to do this fix that I told you about the other day. If you read kernel weights, then it doesn't know that they're kernel weights. So we're making them kernel weights. Because for the hack standard errors, we need to know the kernel weights. And then the last step is here, where we pull the column that we just specified as a dependent variable from the GeoPandas data frame. And here we pull the columns of the two X variables. These are the two ethnic ones. And here we pull the columns of all three, the two ethnic ones with the economic hardship indicator. So then we have everything we need. The first regression I will show you is an absolutely bare bones regression. So this is takes the absolute minimum number of arguments. Actually, the minimum is X and Y and X in that order. But I have specified that the non-spatial diagnostics are false to have a bare bones output. By default, you never have to mess with this. They're always true. So you always have measures of fit and the non-normality, heteroskedasticity, and those things are provided as default. But to show you the absolute minimum, I turn it off. So we pass Y as a dependent variable, X1 as the two ethnic variables, and set the diagnostics to false. Nothing happens. Okay. Actually, what did happen? Remember, this is Python. OLS is a class in Python. I don't know how much Python you know, but we just created an object of that class. So OLS1 is a regression object. It has a whole bunch of attributes. In fact, we can list them by printing, applying the dir command to this object. Dir tells you the contents of what an object has. So this is everything, all this stuff is inside this OLS1 object. And how do we get it out? By the usual notation, OLS1 dot whatever the object is. So if you want the regression coefficients, it's OLS dot betas, right? If you want the predicted value, it's OLS1 dot pred y, and so on. So of course, you have to know what these things are, and that's what manuals are for, right? For our purposes, the main ones are betas, predicted value pred y, variance matrix VM, U regression, the residuals, and R square is the R square. But there is a thing called the summary method, and the summary method lists all the results. So to do the summary method, you get this little output that says regression results, data set unknown because we didn't specify it. In the next example, I will specify it. This is the dependent variable, its mean, its standard deviation, how many observations we have, variables, degrees of freedom, the R square and the adjusted R square, which corrects for the number of explanatory variables. Then you have a little table that lists each variable. You didn't have to specify the variable names in the call because you specified them before, right? And the coefficient estimates, their standard errors, t-statistics, p-value. So you see here, very positive, both ethnicities, very high positive correlation with poor health, okay? And as I said, here we don't have the data set. To get the data set, you specify name DS. Name DS, up on top, we specify DS name. And so now if we run it, we get exactly the same thing, but on top we have data set, the name that we specified on top, right? So this is the same thing. As I mentioned, it's a matter of taste. I like to do it this way. Some people like to do it differently. And then they actually pass the call to the data frame explicitly as the y argument and the call to the explanatory variables as the x argument. It doesn't really matter which way you do it. Either one will work. It's a matter of taste. It's exactly the same result. Okay. Now, to illustrate this immigrant paradox, I'm going to run this again with the economic hardship index included. I run control return, and what we see what happens is the sign of Hispanic flips from positive to negative as a result of including this hardship index. So it's really not so much about the Hispanic ethnicity. In fact, they're in better health once you control for economic conditions. That's just one example of how you have to be careful in running regressions. I can't say this enough because it's so easy these days to run these regressions. People just do it. They just click away, especially if you have, software with a graphical user interface. You just kind of throw variables in, click, click, click. And you have to stop and think what it is you're doing. And especially when you change the specification and coefficients change a lot, then you're in trouble. They shouldn't change much, right? So the summary gives you the estimates and standard errors. It doesn't give you the predicted values and the residuals. You have to pull them out yourself. So now I'm going to illustrate how you do that. As I said, I'm using the regression object with the dot notation. So this is an object in the sense of object-oriented programming. It's an instance of a class. The class is the OLS class in the software, in Python software. So an instance is an example. The class is a template. We create an example using these different arguments, and that example has a bunch of properties. One of these properties is the predicted values. Another one is the residuals. So to see the predicted values, I'm not going to print them out. It's a 791 by 1 column vector. And the residuals, I am going to print them out, not print them out, just the size of them. And the mean of the residuals is 0. That's what you want. If it's not 0, as I said, you're in trouble. And if you want to make a plot or a graph or a map of predicted values or residuals, you have to add them to the data frame. Okay, that's the easiest way to do this. Then you can also write out the data frame and pull it into GeoDa or something else and do other stuff with it, right? So I'm just going to illustrate that here very briefly, where this is kind of combining a number of things we talked about in the previous notebooks. So let's take this apart. We start, the bigger outside picture is we're going to make a data frame using pandas. So that's the data frame command. We're going to pass a numpy array to the data frame command. We don't have the numpy array yet. We're going to make it by using numpy hstack. So we're stacking together the vector of predicted values and the vector of residuals. That becomes an n by 2 matrix. We will pull this matrix and make it into a data frame. And then we give the variable names as columns, predicted and residual. It's your responsibility to make sure that they're in the right order, right? If you're flaky like I am, you might very well flip them around. And then as far as the data frame is concerned, the residuals are the predicted values and the predicted values are the residuals. So this is not foolproof. You have to really pay attention here. And it's the kind of thing that, people like me often make mistakes and put them in the wrong order. So be careful when you do this. And that's why I always like to look at the head of the data frame to see if anything looks funny, right? And you want the predicted values to be in the range of what your dependent variable was, and you want your residuals to be both positive and negative, and so on. So we did it right. And now we have our little data frame with just the predicted values and the residuals. And now we're going to tack that onto the existing data frame. So now we extend our GeoData frame with these two extra columns, and then we can write them out to a shapefile. And I won't, yeah, this is what it just did, actually. I forgot that it's all together. So this part adds the predicted value and residuals to the GeoData frame that we have. And the second one then writes out using GeoPandas to file command. And if you remember a couple notebooks ago, GeoPandas is smart enough, depending on the file name that you give it, to know what kind of format to write it in, whether it's a shapefile or a GeoJSON or something else. So now we have our GeoPandas data frame, and we can do the diagnostic plot that I just showed you in the lecture. We use the plot functionality of a GeoPandas data frame. You can do this much fancier, but this is good enough for our purposes. It's just bare bones. You specify, remember, we have the predicted values on the x-axis. We have the residuals on the y-axis. We tell it it's a scatter plot, and we give it a little title. And what do we get? We get this plot. And so this, if you want to get fancy in Matplotlib, you could also draw a line here, horizontal at 0, which would be the mean. And then in this case, you see kind of a funnel pattern, which would suggest some form of heteroscedasticity. Okay. And then similarly, we can make a map. And we went through several maps in the last notebook. Let me just focus on the command here. Again, we're just using the plot functionality of a GeoPandas data frame. We use our ax notation because we're going to add some things. So we set it up. The variable is the residuals. This is just a size. You can set this to whatever you want. We use the color map, blue, white, red. This is the one I showed in the lecture. We use the standard mean scheme for a standard deviational map. We keep it at we keep it as the default. That means that all the observations within one standard deviation above and below the mean will be white. So those are the good ones where we get a decent fit. We want to show the actual boundaries of the census tracts. We adjust the line width a little bit so it looks a little nicer. We have a legend. The placement of the legend is kind of gobbledygook that I said just copy and paste it. It works. We turn off the box, set axis off. We give it a title, and we show it. And here's our residual standard deviational plot. This is the one I showed you in class. And again, the white ones are where the prediction is pretty decent. Here are positive residuals, so under prediction. Here are negative residuals, over prediction. And what we're looking at is with certain patterns in here. And then one last thing is, before I'll deal with the non-spatial diagnostics next week. This is a requested feature. As you recall, the output of SPReg of the summary is this table, right? Now, if you write a paper, this doesn't copy very well, right? So you have to basically retype it. And we had this problem ourselves. So we figured out, this is fairly recently, that actually the table with the output is a little data frame. I mean, you don't know this, but if you look at the code, you will see this. And so we use the fact that data frames have a LaTeX option. So you can write them as a LaTeX table. And those of you who you should use LaTeX. You know how to do that. There's all these extra symbols in there, which are not that easy. I mean, you can do them by hand, but it's kind of a pain. So this is the LaTeX begin tabular. It sets it up for a table. Obviously, this doesn't look very good, but if you put this in LaTeX and you compile it, it's a very nice looking table. Okay, so in order to avoid having to retype equals typo, right? So this avoids this. Okay, so I'm going to keep it at that. Then next week, we'll look at the non-spatial diagnostics and go over two-stage least squares. And depending on how much time we have, do that notebook as well. But as I said, we'll just do piece by piece and see how far we get.